Section 2.3.2 Analysing substances. I'm sure most of you have seen or done some paper chromatography at some stage. You might have used it to find out how many different coloured inks make up the dyes in felt-tip pens, or perhaps you've investigated food colourings. You should be able to describe how paper chromatography is done, and this is what you need to remember. Start by drawing a pencil line about 2 centimetres from the bottom of a piece of chromatography paper. We use pencil because pencil won't run when it's wet. Place a small spot of colour on the line and put the paper into a beaker containing about 1 centimetre depth of water, making sure that the water level is below the pencil line. We don't want to wash off the samples. Now leave it to run for a few minutes until the water is near the top of the paper. Once we've run the chromatogram, we need to look at it carefully. If we count the number of spots, this will tell us how many components there are in each sample. Here, the purple dye on the left was made up of 3 compounds. If we compare the position of the spots with known substances, and the spots show up at exactly the same height, then we can positively identify these compounds. Instrumental analysis. Why is it better? Well, the specification tells us that instrumental analysis is more accurate, more sensitive, more rapid, and more suitable for use with small samples than manual methods. So, what do you say if a question asks you for the advantages of instrumental analysis? They are more accurate, sensitive, rapid, and only need small samples, of course. Gas chromatography. We use gas chromatography to separate components of a mixture. Imagine you are an elite athlete and the drugs testers come knocking at your door and ask for a blood sample. They will take your blood away, get rid of all the red and white blood cells, and put a sample of the remaining liquid into a GC machine. A few minutes later, all the different substances that were in your blood will be separated, and then they can be checked to see if they have been banned. This is how it works. Firstly, the mixture is injected into the machine. It's then carried by a gas through a long column packed with solid. The components all move through the column, but at different speeds, some faster and some slower, so that by the end, the components are separated. This is what a chromatogram looks like. The number of different peaks tells us the number of different components. If there are 4 peaks, there will be 4 different substances in the mixture. The retention time of a substance is a measure of how long it takes the component to travel from the inlet to the detector. So, if we compare the retention time with the retention time of unknown substances and find that the retention times are the same, then we may be able to positively identify the substances. Just like in paper chromatography, it's the idea of comparing with a known substance which is important. We can be absolutely certain of the identity by using mass spectrometry, and that's what we're going to look at on the next slide. Gas chromatography, mass spectroscopy, or GCMS for short. Mass spectroscopy is a brilliant technique for identifying substances quickly, accurately, and even with the smallest quantities. The really cunning plan is to connect it directly to the gas chromatography machine. When each separated component emerges, it goes straight into the mass spectrometer. This is an example of a spectrum that will come out. Once again, compare it to that of a known chemical, and if the spectrum is the same, the chemical is the same. So it's a quick and accurate way to prove if you have a banned substance in your blood, even in very small amounts. Look closely at the spectrum. The position of the peak on the right tells us the relative molecular mass, that's the MR, of the chemical. That's analysing substances. Next stop, rates of reaction.